طيب بسم الله الرحمن الرحيم. We started IPsec and we talked about the different components for the IPsec standards, including the encapsulating security protocol and the authentication header standards. We also talked about the tunnel mode and the transport mode and when and how to use each of these modes. And also we talked about the bundled security. We talked about the concept of security association, that it's a logical one-way security context, and one way because of the fact that IP is unreliable. And then we talked about the bundled security association, where we can recursively use these security associations in a nested way to accommodate certain scenarios where you want to have these tunnels nested in certain way to provide different levels of security. We also talked about the algorithm for the outgoing packets and for the incoming packets, where we have to check the security policy database and then the security association database. And one thing we talked about is that if we check the security association database, we check it using what we call the SPI. The SPI is the identifier for the security association. So if we cannot find a security association in the security association database, what do we do in that case? We have to establish a new security association, and that's what we have to do today. So if there is no security association, then we have to establish a new one for the first time. So this is the main functionality for the Internet Key Exchange. So the Internet Key Exchange is an integral component of IPsec, where the hosts or the routers or the firewalls, when they establish the tunnel, whether in transport mode or tunnel mode, they have to negotiate some security association. Basically, the outcome is to do user authentication and key exchange. So once we finish that part, we have a complete security association, which defines all the specs for the security keys, for integrity, for confidentiality, for IVs, for anything. And from that, we can do the transport over the tunnel. So IKE is the key management portion of IPsec, which involves the determination and distribution of secret keys. So a typical requirement is 4 keys for communication between two applications. So transport and receive pairs for both integrity and confidentiality. This is the minimum, of course, but we have other things for example, the IVs, initial vectors, and so on. So there are 2 types for establishing the security association. There is the manual and there is the automated. And this is quite similar to, if you remember, we have static routing and dynamic routing. So this is quite similar. So in the manual, the system administrator in that case will establish the security association manual. Okay, will establish this security association manual, and that's maybe valid in the cases of we have like very small network, 2 nodes to secure, to create, like, establish one tunnel between 2 offices, for example, to secure the communication between 2 offices or 3 offices. But if you're talking about an intranet of hundreds of these offices worldwide, then of course the manual method becomes very prohibitive. So in that case, we have to use the automated one, exactly similar to dynamic routing. So in the automated method, we have to perform this authentication and key exchange automatically using some messages that have to go back and forth, and that's what we need to talk about. Okay. So IKE itself is composed, especially IKE version 1. In version 2, they started to merge those 2 components together, similar to merging AH with the ASP that we talked about last time. But in IKE version 1, they talk about 2 distinct methods, and actually 2 distinct components, sorry. So the first component is actually, it's not a protocol. It's called a protocol, but if you read the description, it actually talks about the mechanisms that are used for authentication and key exchange. And it's simply based on Diffie-Hellman. So we studied Diffie-Hellman using the discrete logarithm, if you remember, and we send over the network between two entities. We can send like public keys, اللي هي Y. We can send alpha and Q, and alpha should be the primitive root of Q, if you remember all these things. But there was one issue with Diffie-Hellman. Anybody remembers that? Diffie-Hellman had an issue, right? Had an issue related to what? هتفكر? Diffie-Hellman had a big disadvantage that we have highlighted and we talked about. It's not proof against what type of attacks. So when you exchange these public keys and alpha and Q over a public channel, okay, so this can be exchanged over a public channel, right? So that's doable, and based on that we can generate a shared key between two parties. So that's good. But what can happen in that case, huh?
If there was a man in the middle.
Man in the middle attack. So Diffie-Hellman does not mitigate any man in the middle attack. So anyone can come in the middle and send you, okay, alpha and Q and Y and things like that, and you just accept it and you create a shared key and you start sending some secure information, and he can actually spoof the traffic in that case and can lure the traffic in another way, okay? So Diffie-Hellman had a big issue related to a man-in-the-middle attack. So that's what they needed to fix here. So the scientist who's called Oakley, that's the name of the scientist, who came up with a mechanism based on Diffie-Hellman, okay, using what we call cookies. We'll talk about it. So this cookies concept mitigates the man-in-the-middle attack and the clogging attack as well, and man-in-the-middle attack as part of the key exchange for IKE based on Diffie-Hellman. Okay, so the first component is actually, it's not a protocol. It's called a protocol, but it's not a protocol. It actually talks about the mechanism. So here we'll talk about the characteristics of the Oakley key determination protocol or mechanism that that is used to perform the key exchange and authentication using Diffie-Hellman. The other component is related to the handshaking messages. The other component defines what we call ISAC-MP, or Internet Security Association Key Management and Key Management Protocol, is the actual protocol that defines the message formats. What kind of message formats that get sent from the two parties that are trying to establish the IPsec tunnel, okay, whether it's transport mode or tunnel mode. So here they provide the type of the messages, what type of messages get sent back and forth, and how we can really establish the authentication and key exchange before we start communication. One thing that if you remember, we talked about it, we have an IP, because of the fact that IP is unreliable and best effort and so on, we had the window technique, remember, for mitigating the replay attack. We cannot just have one sequence number or nonces or something like that to mitigate the replay attack. So we have a window, and this window has to be maintained and managed. So there is, in fact, in addition to the data traffic, we have to have a management traffic. Okay, this management traffic will be used between the two parties to communicate anything related to the data traffic. For example, one thing we talked about is that if there is any suspicious behavior for a replay attack that's detected using this window technique, what do we do? In that case, we can send an alert message. This alert message is not actually a data message. It's a control message or a management message, okay? So they realize that we have to have a management traffic, okay, which is on a separate channel other than the data traffic, okay? So this is also part of that protocol, and we have to have these messages, we have to define the format of these messages and so on, which is what we will talk about. And of course, because of the fact that we have this data, we have this management traffic, we have to have also security association for this management traffic, which means that we need to secure the management traffic as well, because it has to go parallel to the data traffic all the time. So the data traffic goes in real time, and then the management message will say, okay, so now I need to change the configuration. Now I need to send an alert that that this traffic has to stop, and so on. Okay. So there are two separate. We talked about the fact that, okay, so we have, this is the host for the, and this is another host, right? And we have to have, whether host or a firewall or a router, right? And we have to have a tunnel, right? So any traffic that goes into that tunnel will be hidden, will be using the security association. And again, we have security association in this way, you have security association in this way, right? It's one direction, right? So this is the data channel. Okay, so in addition to this, there is another small tunnel here, okay, which is for management, okay, for management and control of this data traffic. Okay, it's on a separate logical channel. Of course, it has to go through the routers and everything, but it's logically separate from the data channel. So this channel is where we send a message to configure, okay, and manage the data traffic. Okay, and we'll see some examples of these messages that have to be sent. So tunnel means that this management traffic needs to have also a security association. But we call it that in that case, management security association. Okay, so we have one security association for the data channel, and we have another security association for the management traffic. So we'll talk about how we establish. So IKE is used to establish both. Basically, ISAC-MP protocol is used to establish both security associations. And for both, we need to establish again for each way, right? So we'll see how this is done. That we will talk about. So, أيوة تفضل.
These messages are not bypass messages, right?
Are not bypassed, which means?
It will not pass through the channel.
لا, it's a separate channel. So you have okay, so you have so for the first component here, the Oakley for the mechanism, again it's based on Diffie-Hellman. So we know Diffie-Hellman. We use the discrete logarithm to send public keys in alpha and q and stuff like that between the two entities. But it's good, but it's not enough. So we need to have some kind of a way to authenticate the hosts to each other in order to mitigate any man-in-the-middle attack. It's not just that, actually. There is also the clogging attack. Okay, clogging attack is like a denial of service attack. So you're sending very frequent messages, right, from one host or from multiple hosts to the other end, right? So in that case, we can, in fact, disrupt the communication and disrupt the tunnel by doing that. So also, the mechanism that we're talking about in IPsec mitigates that through the concept of cookies. Okay, the details for that particular mechanism is not detailed in the book, actually, so we don't have to know the details of this, but you can think of it as like you have a hashed value, okay, based on the IP address of the source and the destination and so on, which kind of prevents the fact that you can send illegitimate message from multiple IPs, because if you send very frequent messages from the same IP, it's easy to label that as suspicious, right? Because it's coming from the same source, right? So clogging attack actually is done mainly from multiple sources. So we're trying to spoof, right, the IP address and have what we call a distributed denial of service attack. Okay, so messages coming from different IPs, right? So these cookies actually prevent that, because these cookies is actually, it's like a hard-coded random sequence which is hashed based on some values, which is like secret value between the source and the destination, plus the IP for the source, plus the IP of the plus the port and everything. So if you try to spoof from another IP, the cookies will detect that, because you cannot really hash the same, because again, all the cookies are irreversible. So you cannot reverse engineer these cookies and change it to provide the same message from another IP. So you cannot really perform clogging attack from multiple sources. And if you try to do it from the same source using replay attack, then we can detect it in two ways, because of course we have authentication, which prevents so we have sequence numbers, as we will see, or we talked about it for the window technique. And also, if you send very frequent messages and you try to perform clogging attack from the same source, we can detect that easily, right? So always denial of service is done from distributed sources to appear as if it's coming from different sources, to confuse the receiver. So in any case, so cookies are used to detect the clogging attack. So what else? So of course, the same mechanism uses some kind of authentication, and as we will see, authentication using certificates. They authenticate using certificates, as we will see. So authentication again mitigates the man in the middle attack, which is not done by the Diffie-Hellman. يتبقى بس اللي هو So we have, of course, nonces as well. Nonces are used. Nonces اللي هي number generated once, or number used only once. These numbers are similar to unique sequence numbers, which are generated also using like some random, but these random sequences or these random patterns are always unique, or generated in such a way that is always unique. Okay, so of course, if it's generated like this, so it mitigates the replay attack. So again, we use authentication mitigate man in the middle attack. We use cookies to mitigate the clogging attack, right? And there is also another characteristic which is kind of interesting. They, in fact, use what we call Diffie-Hellman group. Okay, so that's a distinct, unique concept for this mechanism. And what that means is the Diffie-Hellman group, it determines the size of the public key that is used. So of course, as we all know, the private key is a function of the public key, right? Based on the discrete logarithm. If the size of the public key is large, then the size of the shared key is also large, right? So by determining the size of the public key, we can increase the size of the private key, or the size of the shared key. So by controlling the Diffie-Hellman group, we can increase the size of the key, hence increase or strengthen the security. So for example, Diffie-Hellman group 1 uses a size for the public key, uses a size of مثلا 500 bits. Diffie-Hellman group 2 uses مثلا 1024, and then 2048, and so on. Okay, so by increasing the Diffie-Hellman group, this means that the size of the public key is larger, which means that the size of the generated key is also larger, which means more security. Implicitly, more security.
What does it mean, negotiate a group? Two parties negotiate?
Yeah, we'll see that. So you have to negotiate. We have to negotiate the group together. So you say, okay, so can I use Diffie-Hellman group 1? Standards actually define certain groups. It's not like it's not ultimately flexible. لا, so there are certain Diffie-Hellman groups which are defined as part of the standard. We'll talk about this. So it's either group 1 or group 2. So are you going to use group 1 or group 2? And of course, group 2 is used for مثلا classified information. مثلا. So it's used for highly classified information that needs more security. Okay? These are details in the standard that's usually defined based on some requirements from some مثلا vendors or operators and stuff like that. Okay? مفهوم mechanism? Any question about this mechanism? Okay. So this is the handshaking, the real handshaking that happens. Of course, if you look at this again, do not feel bad about this. You don't have to memorize the details of this. Okay, you need to understand it in a pretty high level. But but we can explain it and try to visualize it as much as possible. So basically, this is to negotiate the security association for the data traffic. Okay.
This happened the first step.
Yes. Yes.
So establishing the data traffic before.
Establishes the security association, not the data traffic itself. The security association for the data traffic. Okay. يعني the security context. ماشي. This is to establish the security association for the management traffic. ماشي كده. And this is the actual management traffic. The data traffic is not here. It's not in this. It's not in this graph. Okay. So this is the actual management traffic. So these are the messages that get sent, and this is like ND, and we'll talk about this. Okay. So this is in a high level. Okay. So let's dig down back. So here, in negotiating the security association for the data traffic, so first we send what we call the IKE header, and this header only exchanges the cookies. On the cookies to mitigate the clogging attack. Okay, and then this SAI1, if you see here SAX1, this is the to negotiate the Diffie-Hellman group. Okay, together with the parameter for the Diffie-Hellman, including the public key and alpha and q and so on. These are values that can be exchanged. Okay, so you are saying, okay, so can I use this group? And by the way, this is the public key that I want to use, and this is alpha, and this is q. Okay, is that okay? So this is NI is if you see here, NI is nonces to mitigate a replay attack. Okay. So this will go from one entity to the other, from one host or from one router to the other. Okay. So the reply will contain the same thing, the header to establish the cookies, again to mitigate the clogging attack, and this is the Diffie-Hellman group, and this is for the other direction. This is for the other direction, because here we have to establish security association this way and security association this way, because it's one way, right? So by exchanging these values and these values, okay, so now Diffie-Hellman is done. So we exchange the public key and the parameters, right? So as far as Diffie-Hellman is done, which means that here we already have shared key on both sides, right? We already have a shared key, right? So that's done. But the problem is authentication was not done yet. So this will allow the man-in-the-middle attack to happen, and that's why here we have a certificate request. So I can, okay, so it's like, so the receiver will tell you, okay, so I can play along with you, and I can generate the shared key, but you have to authenticate yourself. Okay, so the authentication happens using the encrypted message, and the certificate will be sent as part of this message. Okay, and also, of course, the source will send a certificate request as well to the receiver. So in this case, we are using the shared key. We are communicating the certificate for authentication, and we are also communicating everything related to this security association. Okay, so using the shared key, we can use it as a master key, and we can generate some مثلا for authentication. What kind of algorithm are we using? For example, the HMAC, we're using SHA-1 for مثلا integrity. For confidentiality, we'll use مثلا AES with cipher block chaining or something like that. So these algorithms are going to be negotiated as part of these values. So these are the values that we communicate to the other party to specify all the algorithms related to integrity, confidentiality, and everything. And at the same time, we send the certificate for authentication. Okay? So this means that the security association at this side is created. Okay? So at this side, the security association is created. So we have to do the same from the other side. Again, we send the certificate, okay, and all the specs for again for confidentiality, integrity, and everything. So in that case, the security association on that side is created. So this way we have done Diffie-Hellman, we exchange shared key, we have used the shared key to encrypt the message for authentication and for the cipher, the security association establishment. So the ultimate outcome for this is that we have a security association for data traffic. So of course, using the same shared key here, we can establish the same for the management security association. So we are also sending the parameters for. By the way, there is a question here. Nonces are used for mitigating. Okay, didn't we talk about replay attack using the window technique?
Yes.
Okay, so why do we have to have nonces here? Eh? We talked about mitigating replay attack using a window and صح? We talked about the window.
It's not established yet.
Yes, bravo Ali. Yeah. So this is mitigating the replay attack as part of the security association establishment. So once we do that, we can use the window to mitigate the replay attack as part of the tunnel, as part of the data traffic, which is not here. Data traffic is not here, aslan. It's not in this graph. ماشي? But these nonces here and here, they are used to mitigate the replay attack as part of the security association exchange. ماشي? Which is different. ماشي كده؟ طيب. So once we create the management security association, as we said, so we have a small logical tunnel which goes in parallel to the data tunnel. Okay. This tunnel can be used for sending management messages, and these messages are these three, basically. But again, the details, there is more details to this which we don't have to get to. So here we have to notify in case, مثلا, we have some alert that through the window technique we have discovered some suspicious behavior that there might be some replay attack. Okay, so based on that we can send a delete message. So these are control messages that control the data traffic, the data tunnel itself. Okay. أسهل كده الموضوع. So at a high level, so these are the components, and this is the details. More than this, you don't have to dig into more details, because the standard itself is like thousands of documents. But we need to understand the concept behind it. ماشي كده؟ So these are the configurations that are defined as part of the standard. So this one is for VPN, which is part of RFC. طبعا you don't have to again to memorize the number. So this is for different parts of the world except for the US. The US has this. This is for the US. It's defined for the US. Of course, the US it's like they need to be different from everyone else. So basically here we have VPN A and VPN B, and these are two Diffie-Hellman groups. So basically you see here, this is 1024 and this is 2048. So the Diffie-Hellman group here uses only different sizes for the public key to again strengthen the security. And as you can see here, so here مثلا you have مثلا triple DES, and here you have AS. Okay, so it's like more secure, okay, with cipher block chaining and everything. Okay, for the US, they have two. These two are again two Diffie-Hellman groups, and this is for classified information, and these two are for unclassified مخابرات بقى شغل مخابرات. Okay, so this is for unclassified information. Again, these groups, they need to be again negotiated at the beginning. So we need to negotiate that at the beginning to start establishing the security association based on a specific Diffie-Hellman group. واضح هنا؟ ماشي؟ في أي لبس؟ في أي حاجة؟ Yeah, so that's pretty much it. So in this chapter, of course, we talked about the overview for IP security. We talked about the benefits for IPsec, how it can be used to secure the traffic between different offices over the internet. We talked about the IP security policy database and how we can use the security policy to route certain traffic into the tunnel or bypass through outside the tunnel for different purposes. We talked about the concept of security associations and security association database. We talked about the two standards, the encapsulating security payload or ESP, and we talked about AH, which we said that in IPsec version 2 it's optional, and you can use ESP for both authentication and encryption. And we talked about how to bundle security associations for different purposes, okay, and eventually we talked about a IKE. ماشي? Okay. So chapter 6 logically goes up to the transport layer. In the transport layer provides what kind of service? It provides the communication between two application endpoints, not routers, not hosts, application endpoints. Okay. Which means that of course we use the security in that layer. It's actually right above TCP, right above TCP. Okay, which means that the TCP header itself is exposed, and then we add a security header, okay, before TCP. So the predominant security protocol in the transport layer is what we call a TLS, okay, transport level security. So initially, TLS was designed for providing security between client and server in web browser, okay, in the World Wide Web services, okay. So why do we need to have a specific tailored security protocol for the World Wide Web? So similar to the fact that we talked about, if you remember network access layer, we talked about specific characteristics in the wireless domain that requires us to look at security in a specific way for wireless. So here, when it comes to World Wide Web as a service, what are the characteristics of these services that requires really tailored security tools? And there are multiple characteristics. منها إن هو the web servers are relatively easy to configure. Why? Because it's based on text. Everything is based on text. So the World Wide Web is mainly based on text. So if you have any web page, you can say display source, and you can see all the text, all the HTML, all the JavaScript, all the CSS. So everything is text, right? It's exposed, right? So that makes it easy to manipulate. So web content is increasingly easy to develop, and it's designed this way. However, ironically, the underlying software is extraordinarily complex. So the web server itself as an engine is highly complex, okay? And it's by design. So it needs to be highly complex to make the higher layer application very easy. Okay, it's like Java. Java is built on this concept. Okay, Java itself as a programming language is very easy, and it's portable through platforms, right? So it's agnostic to the platforms, right? It's not like C++. مثلا. C++ is not easy to port it from one platform to another, but Java is seamless. But in order to do this, we have to have the Java virtual machine, which is highly complex, right? It acts as a layer between the operating system and so this is similar. So web server is highly complex, right? And it provides a layer for the web browsers or the World Wide Web as a service to have very easy content to be developed by different people and stuff like that. But the fact that it's easy to generate, okay, and the underlying web server is highly complex, makes it very easy for people to try to expose or to try to leverage the hidden issues inside the web server by manipulating the text content. واضحة النقطة دي؟ So here, the underlying software is extraordinarily complex. And this may actually hide some potential risks. The fact that it's complex makes it like it hides some security issues that it's not clear, okay? But if you can manipulate the text above it, you can always discover these holes inside that complex framework, right? And that's exposed by everyone. So anyone can actually write like JavaScript and to be able to manipulate the server and maybe utilize some security holes in that server and try to abuse that. Another issue here is that the web server can be exploited as a launching, طبعا because of this, the web server can be exploited as a launching pad into corporation or agencies to entire. So through discovering some holes in that web server, I can use it as a launch pad to the entire network, which is يعني طبعا it can provide very large scale damage. Another issue here is that the World Wide Web is actually used by very untrained users. Even kids are using it, okay? So they can easily be manipulated. So kids can, in fact, go into some weird sites, weird websites. And of course, our kids, they always do that. They like to discover here and there, and they get to some websites that can really provide some security attacks easily, and they can exploit their machines or servers or something like that, and use it as a launchpad to provide some intrusions, and then from there you can provide you can use it مثلا for denial of service attack, distributed denial of service attack, or you can use it to provide other attacks and other damages. Okay, so these are the main characteristics. طبعا the threats, that's not something يعني new. We have threats which are classified as integrity. For the integrity here, we're talking about active attacks, where we actually modify the data message to affect its integrity, or actually modify the browser itself. So we can provide some modifications to the browser configuration, or to the memory, or to the traffic that is going back and forth. So this is يعني some kind of active attacks. So these are the threats, and these are the countermeasures that we can use. Of course, these are clear to us, so we can use some cryptographic checksum or some MAC values to provide some authentication and mitigate any integrity threats. Okay. Confidentiality, of course, uses the eavesdropping, and using eavesdropping, we can, in fact, read some confidential information. So authentication here, we can use the web server to some impersonation to affect the web server. The one that is really by far the trickiest one to mitigate is always the denial of service. So for denial of service, we can perform again the clogging, or some large scale or some frequent messages from different clients to clog the web server, and that's the trickiest to mitigate, because even if you know that the incoming message is not authentic or it's not legitimate, only the processing that you have to do in order to discover that this message is not authentic can in fact slow down the server and can disrupt the service, wasting your resources, right? So if you provide these messages from different sources, that in fact confuses the web server even more and slows down the server. And that's why here for countermeasure, see, it's difficult to prevent. There's no one perfect solution. It's just that we'll see when it comes to intrusion detection, which is the last chapter, the next one. We'll see. The only way you can mitigate this is just to try to put some firewalls in different places. Okay, it's just to try to block this from coming into the network, in order to block this traffic before coming to the network. So this is the only way. But these firewalls as well, they consume resources and they expensive. ماشي؟
So maybe if we apply blockchain, like in Web3, we can prevent this type of attack.
Blockchain itself has very low throughput because of the consensus. Okay, so blockchain is used for certain applications because itself has low throughput because the consensus actually requires overhead to negotiate between multiple parties in order to verify the authenticity of any traffic that is coming in. So it's like you are distributing the processing over multiple nodes, but it still has to be done.
I think this will complicate the exchange between the clients and web servers because the exchange between client and web servers is supposed to be simple, easy, because to enable the connectivity, interconnectivity.
Yeah, I'm not sure how you apply blockchain for web services. This needs to be thought of. But you're right, of course. The one requirement for web services is that it has to be very easy and it has to be fast. I don't want to perform one click and wait for for 1 minute مثلا in order to have a transaction admitted into blockchain before you give me the result. It's not practical Okay. طيب, so these are the different configurations. So when it comes to, for example, IPsec, we talked about IPsec as security from the network layer point of view. This is more often than not is done as part of the operating system itself. So IPsec is built into the operating system. The key here is that it's not tied to a particular application. So even if you use a VPN client, okay, VPN client itself is in fact, it provides IPsec for all the applications in that host, right? But the key here is that IPsec itself is not application dependent by any means, okay? So when it comes to Kerberos usually is implemented in a specific application. Kerberos is actually application level, if you remember. Kerberos is used for, فاكرين اللي هو بتاع MIT ده is used for distributed systems. So Kerberos here is highly application dependent, and it's built as part of the application. Okay. SSL and TLS, we'll talk about SSL now. SSL and TLS, right? This can be somewhere in between. It can be built as part of the operating system because TCP is built as part of the operating system itself, whether it's Windows or Ubuntu or whatever, right? TCP itself is built as a protocol in the kernel of the operating system, right? So TLS can in fact be used as part of the kernel, which means that it's a feature that any application can use, so it's not tied to a particular application. Or it can in fact be embedded into the application. Okay, which means that you open a browser and you say HTTPS, or you open a mail client, okay, and then you configure the mail client to use TLS. So TLS is built inside that application, okay? So it can be as part of the operating system or as part of the application itself. So it could be application dependent or application tied to a particular application, or it could be built as a feature inside the operating system that is not tied to a particular application. That doesn't mean that if it's built as a feature inside the operating system that all applications are by default secure. لا, you have to configure a specific application to use TLS in order to make it secure. Or if you open a browser, you have to say HTTPS, okay, in order to trigger the use of TLS. واضحة النقطة دي؟ Okay. طيب, so
I have a question. Does it mean if the website isn't secure and I put S means it will be will be secure?
yes, but the web server has to support that as well. Maybe the web server is not configured to use TLS or SSL. So in that case, you say HTTPS and you say you put the URL, and then it says no, I don't have TLS or SSL configured. In that case, you will not get a result. Type. So transport layer security or TLS, it was in fact originally built, especially TLS version 1, was built to actually replace SSL. SSL, of course, was اللي هو the secure socket layer, was built on top of TCP under HTTP, right? اللي هو using, when we say HTTPS, we in fact trigger the use of SSL, right, by default. Okay.
So this is application specific?
Application specific طبعا هو TLS and SSL, they are both in the same layer, same level. Okay. But TLS version 1 was in fact designed to replace SSL because SSL had some issues, right? So they tried to design TLS version 1 to replace completely SSL. So ironically, they made it actually not backward compatible to force people to say, no, you have to move completely, forget about SSL and use TLS. But that didn't work so well. So SSL is still being used, okay? So always the backward compatibility concept always wins. So if you try to upgrade, you have to also make it backward compatible to encourage people to switch gracefully, okay? So that's why TLS version 1 did not really find very wide adoption. But TLS version 1.1, I think they started to make it backward compatible with SSL. It's not only that it was highly adopted by web servers and stuff, it was in fact adopted by even email clients and any kind of client-server communication security. Okay, so TLS version 1.1, starting from that version, they start to use it for not only web browsing, for email services, for DNS services, for any kind of client-server service, or actually peer-to-peer حتى, even for peer-to-peer, it's being used. ماشي. طيب. So as we said, TLS either is provided as part of the underlying protocol suite, which means it's built in the operating system, or can be embedded in a specific package or a specific application. We talked about this. طيب, so this is the main architecture for TLS. This is very important. This is the main architecture for TLS, and it's very important to visualize this architecture. So you notice that you have different protocols in the level of HTTP, okay? And you have TCP, and you have on top of that what we call a record protocol. So TLS itself, so we know HTTP, صح? HTTP is text-based protocol in the application level, صح? And it's text-based, صح? It's not secure. So when you say HTTP بس, it's not secure. Everything is exposed, صح? And TCP itself is not, برضو, it's exposed. You have a header and you have the data coming from the application. So we call it a segment, and this is not secure, okay? So when you talk about this, and this, and this, and this, and this, these are part of TLS, okay? So these are different protocol components as part of TLS to allow us to have the application-to-application security. So we need to talk about the details of all these protocol components as part of TLS. It's very important to visualize.
SSL and TLS are the same structure?
Yes, same structure, more or less. Yeah, same structure, more or less. But of course, SSL is much lighter, much easier, and it's primitive compared to TLS. TLS is more sophisticated, but it requires some sophistication. We'll see that. So we need to visualize this. So in order to visualize this picture, I like to have this figure. So we have here a client, and we have the server. Okay. So HTTP itself, very accurately, when we talk about the 7-layer stack. When we talk about the 7-layer stack, pay attention to the question, okay? Which level does HTTP reside in? Layer 7? Application? No. 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 Listen to the question. In the 7-layer stack, not in the 4 layers. In the 4-layer stack, you're right. Session layer, bravo عليك. Yes, session layer. It's not because we have application, we have presentation, we have session layer, right? So in fact, HTTP is a session layer, which means it provides accumulation to the conversation between the client and the server, which means that when I مثلا try to مثلا buy anything from Amazon or from any website, okay? So I click on something, I go to the next page. From one page to another, I need to accumulate some information. This information gets accumulated where? There is something called session context that accumulates the conversation. So first I have to register, I have to put my information. So all my information and everything gets stored into a session context, which accumulates some information based on the conversation between the client and the server. Okay? So here, between the client and the server, HTTP provides some kind of a session context that accumulates through the conversation. Similar to two people are communicating with each other. So I send you some sentences, then you compile it, you put it in your brain as a session context, you accumulate ideas through the conversation. So HTTP is used for that. That's what's called a session level protocol. Okay? By session here, we mean that it's something that lasts through the conversation. ماشي? So when you open مثلا برضو example which is modern, when you open ChatGPT now, so you can write some text. So from one text to another, it accumulates something. So it creates a session. In this session, you accumulate conversation. All the conversation, it's dependent on each other. So you try to accumulate certain information, right? But when you create a new session, خلاص, it does not understand anything about the old session. خلاص, it's like a clear example that you start from scratch. Okay, so HTTP is for conversation. So HTTP itself underneath can, as a session protocol, it creates a TCP connection. Okay, TCP connection. Okay, and HTTP session can in fact instantiate multiple TCP connections. So maybe by click you create a request that goes over TCP connection. Okay, and after this request reaches to the server and the reply comes back to you, this connection is torn down. خلاص. You click, you create another connection, and so on. But the session conversation remains over time. Rather? So one session can in fact create multiple TCP connections. Okay, and that's why in HTTP we have a flag called resumable. Resumable. This means that the session is still valid. So the web server needs to accumulate information. You can create whatever connections you want, but the conversation is still on. If you say resumable equals 0, this means that this request is the final request. So it's like you put everything in the cart and then you say submit, finalize, خلاص. So the session context after that gets cleared. Okay? So this is the unsecure image. Okay? So TLS بقى comes in this picture in two ways. So first, it adds here in the same session, it adds all of these. It adds the handshake protocol, which is what we'll talk about, and this change spec, and alert protocol, and heartbeat protocol. And as you can see, it's in the same level with HTTP. Okay? So here in this header, okay, we have all the information about these protocols, and we'll see how we can do that. Okay? Once this is done, we create multiple TLS connections. Each TLS connection corresponds to one TCP connection. So basically, we create a temporary tunnel, okay, using some specs here, which is we'll see how this is established, okay, and we create a tunnel over TCP. Okay, so this is the TLS connection, and this is the TLS session. We'll talk about this. Okay. طيب so يبقى TLS session corresponds to بقى ايه اللي هو الهاندشيك بروتوكول والسايفر سبيك and so on. And there's the TLS connection, which is the record. The record protocol is nothing but a temporary tunnel over TCP that encrypts everything, but hides everything using integrity, confidentiality, and everything. واضحة النقطة دي؟ واضح؟ تمام. So this is the high level picture. So we'll dig into بقى these protocols. هنا in this picture. In a high level يعني the handshake protocol is the start point. So the handshake protocol is the first one that establishes authentication and key exchange. ماشي? Similar to all the standards that we talked about before. So it sends messages for authentication and key exchange, and this is the most complicated one in TLS. We'll talk about this probably next time. The change of cipher spec. This protocol is very light. It's just you establish the TLS security context in the session, right? But this security context is like pending. The change cipher spec, it says, okay, so use that pending security context as the current security context. So it will be used for all the upcoming connections. So it's like sending one flag to say, I'm going to use this particular cipher spec from now on. This means that all the connections, all the upcoming connections are going to use that particular cipher spec. Okay? And then I may actually renew that at some point based on, as we said, based on certain alert. So if I have any kind of alert using the alert protocol, and we'll talk about the alert protocol, so there are certain scenarios where I discover that there is a suspicious behavior, whether man-in-the-middle attack or replay attack or something like that. So I send some alert messages that the cipher spec needs to be renewed. Okay, so in that case, I have to cut the connection that uses this particular cipher spec and renew the cipher spec again before continuation. Okay, طيب. Heartbeat protocol from the name, it requires the fact that we have to send heartbeat messages. Okay, heartbeat messages. So heartbeat messages, we talked about heartbeat in what context? فاكرين حد فاكر؟ This heartbeat messages حد فاكر؟
To make sure that both parties
are alive. But why do يعني أنا as a client or as a server, why do you need to know that the client is alive? It's that's the closest answer. يعني you are guessing right. What happens is that يعني we'll talk about a scenario, basic scenario. You try to buy something from Amazon, and then you accumulate all the items, okay, and then you get to the stage that you are trying to buy and pay your credit card, and then you start hesitating, and then you leave it. Let me think about it, and you go for مثلا a few minutes or hours to try to think and go talk to your wife or to get the permission and so on. So during that time, the conversation is idle, صح? The session is idle, right? What might happen in that case is that the firewall can invalidate the session. Okay, and that's why we see when we try to browse, especially in the yes, you start to click and then you say, okay, no, خلاص, the session expired. You have to try, right? So in order for the server to configure certain timeout before it expires the session, okay, it needs to maintain through the firewall that this session is valid through that time. Okay, so for example, I need to make the session valid مثلا for 20 seconds, for 30 seconds, for 1 minute. Okay, I don't know when the firewall is going to invalidate the session. So in order to guarantee that, I have to send heartbeat messages to tell the firewall this message is valid. This session is valid. This session, even if you're still thinking about buying or not buying, yeah. So it actually keeps the session valid even if the session is idle. ماشي. So this is how to understand how they work. So this is what we have explained. So we have the concept of TLS connection, okay, which is nothing but a temporary tunnel over TCP that encrypts everything, but using some cipher spec or using some similar to security association. يعني هنا we call it cipher spec. ماشي. So using cipher spec, right, which is as part of the session, established as part of the session. Okay, so TLS session, in fact, has multiple TLS connections. So the relationship is one to many. So one TLS session has multiple connections. So that's how it works. Okay, so the connections here are transient. So it may actually get established and then torn down. So each TCP connection will have one TLS connection or one TLS tunnel that goes with it. واضح كده؟ Yes, but of course, as we will see, يعني, we don't have to establish a cipher spec for every single connection. No, it doesn't work this way. Okay, so we may in fact use cipher spec for multiple connection, because establishing this for every single connection is a big overhead. We cannot do that. Okay, that's why the TLS session context or the security context is maintained at the session level. ماشي. So we'll see about how this is done. ماشي. هي دي. They are used to avoid extensive negotiation of new security parameters every time. That doesn't mean that once we establish the security context that it's permanent. No, there are certain scenarios through which we can decide, no, we have to. But this is not based on creating multiple connections. No, it's based on some alerts. That's why we have what we call alert protocol.
Or a lifetime, maybe.
Or a lifetime, yes. So we can have certain events or incidents that forces us to renew the security context. Okay? A high level. Remember here, until now, one thing unique, one thing يعني, distinct that we didn't talk about here, we did not talk about database and security session database and صح? A policy data. Why? برافو عليك. Yes. يعني خليكي confident كده. Why? صح بالضبط. Because here it's يعني in IPsec we need to create a tunnel that secures for all traffic, all types of traffic. But here no, it's one application, one type of traffic. Okay, so we don't have to have a security session database and لا خلاص. We don't have to have that. طيب, so a session state is defined by these following parameters. So of course we have similar again to security session. Security session we identified using SPI, right? So this is here we call it session identifier. So this session identifier gets communicated between the client and the server. Okay. It's an arbitrary sequence chosen by the server to identify an active or resumable session. And we'll talk about resumable session, why we need to have, or actually we talked about resumable session. It's like the conversation is continuing, صح? Peer certificate. The peer certificate, as we have talked about before, the certificates, they are used to communicate a public key. So if we have the peer certificate for the client, the peer certificate for the client has the public key for the server. And the peer certificate for the server has the public key for the client, right? Compression method. Why do we need to have compression? Compression method. We all know compression, صح? Why do we need to have compression here?
To reduce the overhead.
To reduce the overhead of what?
Data traffic.
Of eh?
Data traffic.
Encryption.
Of encryption. برافو عليك. Yes. ناس صح ما شاء الله. So yes. So as we of course. يعني I hope you appreciate that through assignment 1 يعني security itself as encryption and authentication, it has some kind of overhead, of course, right? So one way to try to compensate for this overhead is that when we get the data, we compress it before we start encrypting. By doing this, we reduce the data size. Okay, so when we reduce the data size, we apply encryption on a small data size, so the overhead of encryption becomes smaller. And also the data that we send over the channel is smaller. But what kind of compression are we talking about here? Of course, lossless compression. So we cannot under any circumstances lose any information from the traffic. So this is and by the way, compression is, as part of TLS, is optional. is optional. Again, it's an option that you can use to it's a flag يعني it's one of the configurations. You have to say compression yes or no بس. Okay, if you have compression, then you compress the data before you encrypt it or before you provide any kind of authentication. The cipher spec, this is the most important one. This is the specification. It's like similar to the details of the security association. Here I have to store the mechanisms that I have to use for encryption, for integrity, for IVs, for RFP, layer pseudo-random functions, for all of this. So I have to have these specs as part of the cipher spec. And we have the master secret key, okay? This master secret key from which we can extract all the other keys. We'll talk about برضو many keys here, similar to فاكرين wireless. We talked about many keys. Here برضو we'll talk about some other keys for different, yes, for securing the different, for creating different keys for different security services. And here we have is resumable. Is resumable again is used to indicate whether this session is continuing or this session is stopping at this point, which means that the security context will have to be renewed and cleared. So this is the connection state, and the connection state is defined by the following parameters. So interestingly speaking, we have what we call server and client random sequence. So we'll talk about why we need to do that. This is quite unique for TLS. It's not being used for other protocols. But as a standard, we have the server write MAC secret and the client write MAC secret and the server write key. When you talk about key here, this is for encryption. So you have key for encryption and the key for MAC. ماشي؟ So message authentication codes, right? And we have client write key and initialization vector. So basically here what we have is so when we say server write, this means that this is the key that's used from the server to the client. Okay? So it's like this. So you have the client and you have the server. So server write, this means that here in this direction, server write, okay, we have MAC key, right? And we have encryption key, and we have key for also IV, initial vector. Okay, or random sequence for initial vector. All of these, by the way, are extracted from the master secret key. Similar to wireless, okay? So remember, these are shared keys. When we say master write, this does not mean it's a public, these are shared keys, okay? These are shared keys which are all extracted from the master secret key. Similarly, when we say client write, this means that here also we have MAC and we have encryption and we have IV. Okay, from the client to the server. So when we say server write this direction, client write this direction. And of course, sequence numbers, of course, TCP itself has sequence numbers, huh? Why do we have to have sequence number here? For a replay attack, for mitigating replay attack. Okay. But here we don't have a window. Why?
Because it's reliable.
Because TCP is reliable, it's connection oriented. Okay? خلاص, data is in order. Order ما فيش تهريج فيه. Order. Okay? So TCP will guarantee the order delivered for us and the reliability. And because of the fact TLS works on top of TCP. ماشي? Between TCP and between the HTTP. ماشي? So we talked about, I should have طيب, starting from here we'll talk about the different protocol. The one that's most important is the record protocol. Record protocol, again, it provides two fundamental services اللي هما confidentiality and integrity. طبعا the handshake protocol defines the shared secret key through the handshake protocol. The handshake protocol هنا explained that before. So the handshake protocol here defined by the first exchange, which generates the cipher spec and the master session key or the master secret key. From that key we generate all the other keys using بقى اللي هي pseudo random function عادي يعني. ماشي. برضو the handshake protocol provides the key that we use for A4 Max. So these are the two services provided by the record protocol. So this is the sequence. So this is how we perform the record protocol, assuming that here we have the cipher spec ready and we have all the keys. So what we need to do in the record protocol is that we take the application level data, which is like big web page, video, whatever, and then we break it down into I like to call it segments. I don't like this this name. So we call it segment, not fragment. ليه بقى? Fragment is like a network layer concept. So I don't want to I like to give it a proper name. So we divide the application level data into segments, right? And then we take this segment and optionally we can compress it. By compressing, we reduce the data size. By reducing the data size, then when we add the MAC and we provide the encryption, we sort of reduce a little bit the overhead required to do the MAC and the encryption and so on. Well, okay?
Isn't the segment same as the packet? Or?
No. Segment is a transport layer. We call it protocol data unit. A transport layer protocol data unit. The packet is a network layer protocol. So packet includes the IP header. Segment includes only the TCP header, up to the TCP header. واضح? But here actually, in fact, we'll add the TCP header after this. So TCP header comes after this here. Okay, so first we have the TLS. This is the TLS header. So after we encrypt and everything, we add the TLS header. The TLS header, as we will see, it's very simple. It only defines the message type, because this message, it might be a data message or it might be any of the protocols that we talked about, handshaking or alert protocol or whatever. So we'll see. So that's how it looks like. So the header itself, this is the TLS header. So it has the content type, and this content type could be data or could be any other control or session level message type. Major version and minor versions, so I don't know why they have it this way, because if you have TLS 1.1, so the major is 1 and the minor is 1. Or 1.2, so the major is 1 and the minor is 2. I don't know why you would need to have two fields for that, but that's part of the stem. And then compressed length. Why do we need to have compressed length بقى?
To know when the message, where the message is and where the MAC is.
Use it for uncompressed.
Yeah, because it's different size.
The compressed length is in fact up to here. Okay? Before the MAC. So there is something here. ايوه كده برافو ايوه ده ايوه صح. So this is a random padding. Yes. So this is random padding. Again, random padding is for to confuse the traffic analysis. Okay. So of course, because there is random padding, it might be variable, صح? It might have variable size. That's the whole point of random padding, and that's why you need to keep a compressed length. Okay. TCP defines the whole length of the segment. Okay, so I know the length of the MAC and I know the length of the segment, but here is just to account for the random padding. ماشي كده? So these are the different types بقى, اللي هي content types. So you have 4 different types corresponding to the 4 different protocols. So you have the change cipher spec, and as we said, change cipher spec is very easy. It's just a flag that says use the pending cipher spec as the current cipher spec. That's it. Very easy protocol. There's nothing to it. ماشي? Alert protocol, as we said, alert protocol is used to again provide some level of warning or fatal error, okay, or suspicious behavior that requires the fact that this cipher spec needs to be stopped and it needs to be renewed right away. Okay. The handshake protocol provides this message from us is very complicated. We'll see different messages. These are used again for authentication and key exchange between the client and the server. Okay, we'll talk about this probably next time. And طبعا the most common, which is the data, to secure the data itself. So this is the message type for the data, which could be طبعا HTTP and could be طبعا email could be anything else. So these are the 4 content types of the TLS header. So isn't the TLS protocols, you have the change cipher spec, and this is very simple, value of 1 to indicate that pending cipher spec is the current cipher spec, which means that all the upcoming connections will use that cipher spec from now on. Alert protocol is used to convey TLS related alerts to peer entity. So I need to inform the server, or the server needs to inform the client that there is some kind of suspicious behavior. And this suspicious behavior could be on 2 levels. So you have the level, which could be a warning or could be a fatal error. Warning means that it's just a warning. I'm noticing something, but it's not really a fatal error yet, so you can continue. It's just a warning, okay? Fatal means that so here, the warning to convey the sensitivity of the message. So if the level is fatal, this means that TLS will immediately terminate the connection, okay? Will immediately terminate the connection that uses this particular cipher spec, okay? Other connections on the same session may continue. And what that means is that here, by the way, there could be, TCP itself may in fact provide multiple connections going at the same time. For example, if you are downloading files, okay? So each file, مثلا, using over HTTP will in fact use a separate connection. And all of the connections will go in parallel, okay? So in that case, these connections, they might use different cipher spec for this case, okay? So if particular alert is providing an alert for one cipher spec, this connection will be terminated, but other connections may still continue if they are going in parallel. ماشي? It's a very specific scenario anyway. Handshake protocol allows the server and the client to authenticate to each other to establish the authentication and key exchange, and that's a sequence that we will talk about next time. It's fairly complicated, as we will see. That's the one. So we'll start it next time, because this one requires